So hello friend, good evening to all of you. So today I am going to discuss about the third lectures of this pericyclic revisions lectures, and these lectures I have completed 2 lectures, revision lectures, pericyclics, which I have done in types of basic introduction of pericyclic reactions, as well as type of pericyclic reactions like electrocyclic, cycloaddition and sigmatropic. And now in this lecture I am going to discuss about other sigmatropics like rearrangement, co-rearrangement, rearrangement, as a co-rearrangement. So these are the other sigmatropic rearrangement reactions is also very important through exam points of view. So before we start to this lecture, so my request, please, if you have not subscribed my channel, so please subscribe my channel and click the bell icon so that you will get the easily notification time to time, and share with your friend. Okay, now we will start. So in this lecture, basically the other sigmatropic shift are rearrangements. So what is the other sigmatropic rearrangement? First one is like Cope rearrangement, second Claisen rearrangement, third is Claisen Cope rearrangement, and fourth is as a Cope rearrangement. So I will discuss one by one. So first I will discuss Cope rearrangement, and these are very important. There are several questions in different exam examiners have been asked. So first I will discuss Cope rearrangement. So what is Cope rearrangement? So it is basically the 3 sigmatropic process. Okay, and it undergo thermal rearrangement, like it undergo thermal rearrangement. Okay, and here basically we choose the 1,5 diene. Okay, and this will undergo 3 sigmatropic rearrangement. That is all things we call the co-rearrangements. Okay, as I told, this reaction is favorable under thermodynamically condition. So if we take the examples like this, so this is 1,5-diene, one, you can count here 1 2 3 4 5 6. So this is 5 position, this is 1 position, so this 1,5-diene. So okay, so here the sigma 3 sigmatropic rearrangement take place. So counting will start 1 2 3 1 2 3, because 3 is the addition, means okay. So 3 sigmatropic rearrangement will take place. So new bond will form. This is the new bonds. Okay, so here the new bonds will form and reaction undergo like this. Okay, and this bond will break. So here this bond will break, this bond will form, so it will look like this. Cn, and this form double bond, here the single bond, this is also double bond. So this is the product. Here this is new sigma bond. Okay, so this is the co-rearrangement. So if we talk about stereochemistry, so stereochemistry of this co-rearrangement, basically it undergo through chairs like transition states, and this rearrangement of meso-diene through such transition state, then it would give the cis trans isomers. So this will give cis trans both isomers. If you see stereochemistry, it is basically undergo chair form. Okay, here the methyl group, here hydrogen group, here methyl group, here hydrogen group. This is a meso form. Okay, under heat condition it will go like in transition state way, like one bond form like here and one form here. This is breaking bond, this is the breaking bond, this is formation bond. Okay, so these are the transition state, and here the, so this is the transition state of your reactant, and product will form like this. Double bond CH3H. Okay, so this is the product. So here says the cis trans stereochemistry will form. So if you see here, this spaces, this hydrogen for this carbon hydrogen is just opposite, and here is just two, these are the trans. So here is trans, and if you see here, this hydrogen H and this hydrogen H, so this is cis. So here the will get the cis and trans isomers. Okay, so stereochemistry is happen like this. Now I will discuss about the Claisen rearrangements. Okay, so what is Claisen rearrangement? Claisen rearrangements number 2. Claisen rearrangement. So Claisen rearrangement is also happen undergo 3 sigmatropic rearrangements. This is first sigmatropic rearrangement which discovered okay, and when the allyl phenyl ether is heated undergo without solvent, then product will be orthoallyl phenol or para product. So here reaction will undergo through allyl phenyl substrate ether under heat condition without solvent. Okay, so this is the first condition for the Claisen rearrangement, and it will form the ortho and para product, but ortho product will be the major product, then para. Okay, so if you see this example for this, so this is O, this is phenyl group. Okay, this is allyl group, this allyl group, this is phenyl group. Okay, so here says the phenyl ether, allyl phenyl ether they have taken under heating 3 sigmatropic rearrangement under heat condition. Then 3 means you have count from here 1 2 3 1 2 3. So this will go like this, this will go like this. Okay, so it will break like this. So here what you will get? You will get the product like this. This here you will get double bond, here you will get this new sigma bonds, here 1 2 3 carbon, so 1 2 3 carbon, so 3 carbon here you will get in last carbon sigma bond. So this is the product, this is ortho product. Similarly you will get para product if both ortho product are mean the ortho position are occupied. Okay, so similarly, if you attack further these spaces, if you write these spaces in this way, this, okay, like this. So here if you write so, if you see here, so the here is also will get the 3 3 1 2 3 and 1 2 3 2 3. Here you will get the sigma tropic 3 3 sigma tropic. Okay, so there will be this will be attack to this position, and this will go this, and this will be back this, like this. So you will get the para product. So para product like 1 2 3 carbon. So you will get the these types of products. Okay, this is para product. So this is para product. Okay, hopefully you understand what I am trying to explain. So in both way you can shift the allyl group with ortho as well para, attached to ortho as well para position. Okay, so now there are 3 cases when case 1, if the both ortho position are occupied, then obviously the allyl group will shift to the para position. If both ortho and para position, if both ortho position is fixed, then move to the para position, and if both ortho and para position fixed, then there will be no chance of this rearrangement happen. Okay, now I move to third, Claisen Cope rearrangement. So what is Claisen Cope rearrangement? So it is basically observed in allyl vinyl. This observed in allyl vinyl ether. Okay, but here observed in allyl phenyl ether. Okay, here observed in allyl phenyl ether. Here observed in allyl vinyl ether. So if you see examples, because in chemistry without organic chemistry without example you will not understand what the actual statement is saying. So if you see, this is allyl group, this is allyl group 3 carbon, this is vinyl group 2 carbon. Okay, so if you count 1 2 3 and 1 2 3, so here is also happen 3 3 sigma tropic under heat condition. So it will go like this. So what will happen? So here the product form like this. Okay, so here this is new sigma bond. Eliankov rearrangement. Now discuss the fourth one, last, Eliankov rearrangement. So what is Eliankov? Eliankov is basically, if you see, guess the idea. Aja means some nitrogen group in between the alien and vinyl group. So like 2 degree, 3 degree. So this is the Eliankov rearrangement. So if you see the examples, here's N, your N, and your here the allyl group, and here the vinyl group. Okay, this will go under heat condition 3,3 sigmatropic. So product form will like this. This is N, this is double bond, this is double bond. So this is all about the other sigmatropic shifts or rearrangement. So these are the 4 types of sigmatropic shifts. Okay. Now I will discuss the other things. Other things means which is very important. Photochemistry. This is the last part of this pericyclic reaction, and which is very important. Inside this I will discuss the principle and application of photochemical reaction, which is basically is this part is also comes in organic chemistry. Okay, so now we'll start photochemistry. This part is very important. Photochemistry of organic chemistry. So what is photochemistry? Okay. So if you see, photo means some lights. So this reaction will move forward under if light absorbed. Okay, so this is also the concerted photochemical reaction, okay, between two olefin leading to the cycloaddition, to a cyclo addition. Okay, if you see examples, see this undergo accumulate, so form this cyclic product. So here you are seeing you choose to olefin which is leading and cyclo addition, so this will form. Okay, so points to phosphorescence is represent as like this transition happen from triplet to singlet ground state plus accumulate is released. So this is phosphorescence. Okay, so this is phosphorescence. So actually this is the forbidden transition. Why? If you remember the selection rule, so the selection rule says the if the transition is delta S is equal to 0, then this will be the allowed transition. If this does not 0, this forbidden. Okay, so here triplet means 2s plus 1 is equal to 3, so implies S is equal to 1. But similarly for the case of this singlet ground state, 2s plus 1 is equal to 1, it is implies that S equal to 0. So delta here, delta S is does not equal to 0, so this is forbidden transition. That's why this is the forbidden zone. So actually this fluorescence is happen through forbidden transition triplet to singlet state. Okay, so now we move to another points which is very important. Another point is like 3 nourish type first. So what is nourish type first? This reaction also undergo light HMA condition, and here basically the decarbonylation reaction happen at the that means the loss of CO. Okay, and form the diradical triplet intermediate. Okay, so this is the main important points. So if you see these things also through examples, so examples number 1. So if you see through this example, so this is methyl and this is carbonyl, this is below the plane methyl. So and what it said, decarbonylation reaction happen through loss of CO, form diradical intermediate. So here form the diradical intermediate, and this will go under HMU condition. So if you see here, you can break like this bond or this bond. Okay, so I will break this bond, okay, not this. So what will happen? This will happen like this. This is methyl, this form radical, and this here also form radical. This is below the plane. Again this will break like this. So this is the diradical intermediate, and again form the this 5-member ring. So this is the product. So actual theme of this Norris type 1 is this. Okay. There are several examples you can solve inside this Norris type of 1 reaction. So another examples, if you see here, example 2. So here basically the decarbonation of happened under HMU condition. Okay, so here you break this bond. Okay, so here also form the radical. Okay, so here form radical, this form radical, and this will break also, and this will form like, and this on this. So this is the actual product. Sorry, this is the actual product. Okay, this things will remove, and here create radical. This radical will combine this. Okay, and this thing will not happen. So product will form like this. Okay, hopefully you guys understood what I am trying to explain you. Okay, now move to another things. Norris type. Norris type 2. This is also very important. So Norris type. So 4 points is Norris type 2. So this is also very important, and it will undergo under light condition. So here is point is number point is 1 is cleavage reaction happen, and this undergo the intramolecular abstraction of gamma hydrogen followed by cyclization of diradical. Okay, So these two point you should always keep in your mind, then after you can solve the problem. So we take examples here. Examples, this is very basic examples. Here pH, here your CH, 2H, and here your carbonyl. So if you count here alpha, this is beta, this is gamma. So here what it says, cleavage is happened, but intramolecular abstraction gamma hydrogen it will abstracts. So this cleavage happen, but intramolecular means this hydrogen will abstract. So this hydrogen will abstract to this position. So this will form 1 2 3 4 members rings. Okay, so here this is your nitrogen and this is your pH, and okay, so here your OH and here your pH. So this is the product. Okay, so here basically the gamma hydrogen is abstract. So first you choose where your gamma hydrogen, from which position you will get gamma hydrogen. Okay, then you can easily solve the problem. So now take another example, then you can easily understand. Okay, these examples, if you take example 1, this is 2, and this example is very good example. So it binds like this. Okay, and here this binds like this. Here then this is 2 hydrogen. Okay, and here carbon and here pH. So if you count here from this, here alpha, beta, this is gamma, this is also beta. You have two way. If you either you go like this, either you go so here you will get gamma. So both way you can get gamma hydrogen abstraction. So under HMO condition, this cleavage will happens. Okay, this cleavage will happen, so create the radicals. So here create radical. Okay, so here you will create the radical. First create the radical. Create the radicals. Okay, and this hydrogen abstract this carbonyl. So this will come here. Okay, and one radical remain here. Okay, now this radical, here one radical is remaining. Okay, one radical this is remaining, so this will break and this radical form double bonds. If you see here, this is form double bond. Okay, and this this is your also double bond. Okay, this is your double bond. Here you will get double bond, and this here this pH. So basically you get the 5 membered here rings. Okay, after tautomerization you will get the product, means tautomerization like this, you will get the product. Is this. Okay, this is your final product. Okay, so hopefully you guys understood what I explain you. So this is the basically revisions. So next lecture you can also solve problem yourself more and more related this theory, so that you can easily understood. Okay, thank you, bye bye guys, take care, good night.